Today's lesson on 2.4.2 is going to be on Descartes' rule of signs. Descartes' rule of signs is designed to help us figure out more specifically what types of zeros we could have in a polynomial. So the basic premise behind this is that you can actually look at the signs of the function and use those sign changes to determine different characteristics of the zeros of the function. So the first rule says that the number of positive real zeros will be equal to the number of variations in the sign of the function, or less than that number by some even number. Okay, and that sounds a little wordy and kind of peculiar, but once you see what it means, it's really simple. For the negative real zeros, you're going to do the same exact process. You're going to look at the number of variations in sign, but you're going to look at the number of variations in sign of f of negative x. So you have to change all of your inputs to negative x, and then simplify, and then see the sign changes. So, excuse me, it's a fairly simple process. We'll start with this first example. G of x is equal to negative 3x cubed plus 2x squared minus x minus 1. So when we say the number of variations in sign, that means any time that the terms change from negative to positive. So if we look here, our first term is negative 3x cubed, and then our second term is positive 2x squared. So that counts as a sign change. And so if you want to, you can mark that in there that this is one sign change. And then from positive 2x squared, we go to negative x. That would be a second sign change because we had a positive term and then a negative term. So that's two sign changes. Now negative x, the next term is still negative, negative 1. So that does not count as a change in the sign. So over this whole polynomial, there are two sign changes. So that tells us that there are either two positive zeros or it says by some even number less than that. So even numbers less than 2 would be 0. So either 2 or 0 positive zeros. Okay, that's the first part. Descartes' rule of signs also wants us to determine, to describe the possible negative real zeros we could have. So we could either have 2 positives or 0 positives, or let's see how many negatives we could have. So now we have to slightly modify our function. Instead of doing g of x, we have to do g of negative x. So I'm going to replace all of my x's with negative x. So this is negative 3 times negative x cubed plus 2 times negative x squared minus negative x minus 1. And then we want to simplify. So g of negative x can be simplified. Negative x cubed would be negative x cubed. A cube does not change the sign for the base. But then I'm going to have negative 3 times negative x cubed, which is going to change this to positive 3x cubed. Negative x times negative x is positive x squared, so this is going to be positive 2x squared. Negative negative x is positive x, and then we still have our minus 1 at the end. So now when we track our changes in the sign for this new g of negative x, that's not a change. That's not a change. Here's our first change when we go from positive x to negative 1. So that's one change in our negative function. So that means we have one negative 0. And then we would normally reduce this again by some even number. But 1 is as low as we can go. We can't have negative 1 negative zeros. So at this point we realize that we have to have exactly one negative 0. And that's pretty useful information. That could help us when we're trying to find our possible rational roots. So for the practice problems, all you're going to have to do is describe the possible zeros. They're not asking you to find any of them. And so your description will just simply say how many positive zeros, how many negative zeros. This one has either 2 or 0 positive zeros. This one has 1 negative 0. Okay, so let's try these two. Remember, before plugging in the negative x, find the number of sign changes. And then that'll be used to describe how many positive zeros you have. Then replace the x's with negative x and count the sign changes. And that'll describe the number of negative zeros. Okay, for 5a, you should have gotten that there was one sign change. So that means there's one positive real zero. Okay, when you replace the input x with negative x and simplify, you should have gotten 1, two sign changes. So that means there's either 2 or 0 negative zeros. Notice that these are only talking about real zeros. In a second, we're going to talk about how you can have imaginary zeros. This is not including those. For 5b, we have 1, 2, 3 sign changes. So make sure you caught all of them in this polynomial. That means you have 3, or remember, some even number less than that. So all of your even numbers less than 3 would just be 1. So the next thing we're going to be looking at is how to write our own polynomials if we know the zeros. This time, though, we're not just going to be considering rational numbers or even just real numbers. We're going to consider complex, real, all of the types of numbers that you could have as a solution to your polynomial. And so because we're going to be dealing with complex numbers now, we've got this theorem called the conjugate root theorem. A conjugate number is a number that combines real and imaginary numbers. It's usually found in the form a plus bi, where I is the imaginary number. A complex conjugate would be, remember the definition of conjugate is when you switch the sign. So instead of a plus bi, you have a minus bi. That's the definition of a conjugate. So the conjugate root theorem says that if you have a root that says a plus bi, you also automatically have to have a root that's a minus bi. They go hand in hand. So you can't have one root without the other. Now remember, these aren't going to be x-intercepts because these are actually imaginary. So it's not going to be a place where the graph crosses the x-axis, but it will be a complex solution to our polynomial. And we can also use them to construct polynomials. So that's what we're going to be doing for example 6. The last thing I wanted to talk about is something that's called the linear factorization theorem. Okay, so if I give you a list of zeros, you should be able to write the factors. If my list of zeros would be C1, C2, C3, all the way up as many factors as I give you, you can create the polynomial by foiling and distributing all of the factors, x minus C1, x minus C2, all the way up to x minus however many zeros I give you. Now that being said, there could be some constant in front that we're multiplying by, we just don't know. We usually call that a, but honestly, as long as you have foiled all of the binomials correctly, that's good enough for me. So for example 6, it says to write a polynomial function of least degree with real coefficients in standard form that has -2, 4, and 3 minus I as zeros. So the first thing we should notice is that we have 2 real zeros, -2 and 4, and we have one complex imaginary one, 3 minus I. Now according to the conjugate root theorem, if 3 minus I is a 0, that automatically means that 3 plus I has to be another one. So now we see that we have actually 4 zeros. We have -2, 4, 3 minus I, and 3 plus I, which means I have to have 4 factors. We don't want to create any more than that because it says to create one of the least degree. So the smallest degree we have will be 4. And so to write this function, we'll call it f of x. We're going to write all of our factors for these zeros. So the simplest way to do it is to make sure that you are writing the opposite of whatever your zeros are. So I'm going to write x minus -2. We really know that x minus -2 is x plus 2, but by making sure that we write the subtraction of the zeros each time, we won't make any mistakes. So x minus -2 is one of my factors. X minus 4 is another one. And here's where it gets a little bit tricky, because now we have to do x minus 3 minus I. Make sure that the 3 minus I is in parentheses and that you're subtracting the whole conjugate from x. And then our last one is going to be the 3 plus I. So x minus 3 plus I. Okay. And so we can simplify this a little bit. Subtracting a negative becomes positive, so we know this becomes x plus 2. And this is x minus 4. And now this part, you always want to FOIL together your complex numbers first before you start trying to combine them with your real numbers. If you multiply the imaginaries together, they should cancel each other out very nicely. So let's try this. X times x is x squared. X times -3 plus I is -x times 3 plus I. Negative 3 minus I times x is going to be negative x times 3 minus I. Those are my two middle terms. And then lastly, we have negative times a negative. So this is going to be plus 3 minus I times 3 plus I. Okay. Now we have like a miniature FOIL one in here. This one should work out pretty nicely because they're conjugates. So 3 times 3 is 9. 3 times I is 3I. Negative I times 3 is minus 3I. Those go away. And then negative I times I is negative I squared. That's going to work itself out to be a real number again. So the 3 i's cancel. And then negative I squared, remember I squared is negative 1. So this becomes 9 minus negative 1. We need to distribute our x's in here. This is going to be minus 3x minus ix. This is going to be minus another 3x. And then plus an ix. And so I'm just carrying everything down. And so a lot of this will cancel out. Notice you have the minus ix and the plus ix. If you do things right, all of your imaginaries should go away, and you're just left with x squared. Minus 3x combines to minus 6x. And then we have our plus 9 minus negative 1. So for our final part over here, this is x squared minus 6x. This changes to adding the positive 1 plus 10. And then we have our original two factors over here, x plus 2 and x minus 4. So we still need to continue foiling. X times x is x squared. X times negative 4 is negative 4x plus 2x minus 8. We'll combine those terms. This is x squared minus 2x minus 8. That's my first quadratic trinomial. My second one is x squared minus 6x plus 10. And we have to do one last distribution. This is a 3-term times a 3-term, so we've got to distribute 3 different times, 3 ways. So x squared times x squared is x to the 4th. Again, we said it was going to be a 4th degree polynomial, and there it is. Minus 6x cubed plus 10x squared. And then distribute the second term, that's minus 2x cubed plus 12x squared minus 20x minus 8x squared plus 48x minus 80. Okay, so there's all of our terms. X to the 4th. Let's see, we can combine these two cube ones. This is going to be minus 8x cubed. 10x squared plus 12x squared minus 8x. So that's 22x squared minus 8x is going to be 14x squared. And then lastly, we have our minus 20x plus 48x is going to be plus 24x. I'm sorry, plus 28x. And then minus the 80. Okay. So there is our function polynomial of lowest degree with all of our factors spoiled out. That's your answer. And again, this could be multiplied by some constant. So if you wanted to, you could say, or you can multiply by any constant a as well, and it would still have those same factors. But you don't have to do that. You can just leave it in its simplest form. Okay, try these two on your own. Notice that 4i is a complex number. We usually don't write it like this, but you can think of it as 0 plus 4i, which means you'll also have the complex number 0 minus 4i. And because they told you that 1 has a multiplicity of 2, make sure that you include that twice. So you'll have x minus 1 and x minus 1, both in yours. Okay. Same thing with 6b over here. Give those a try. I'll put up the answers right at the end.